Good afternoon, everyone. Let me know if I'm audible and my screen visible.
Yes, sir.
Yes, sir.
Thank you. Today we'll start. I believe last lecture we discussed router architecture. What did we discuss in last lecture? That was on Monday. Anyone? So no one remembers. Good guys, if you don't remember, good luck to you. I don't know how will you do. My recommendation is please refresh what we study. Don't keep it pending till the end date. But that's your choice. So let me continue. We will look at link state routing, a routing protocol that is used to build routing table. So primary purpose of any routing algorithm is when we have a network which has many routers, and that means many small networks, and different routers are connected by many links. How do you find out what is a good path from a one source to a given destination? And how to define the good path? We can say good path is the least cost. And then question comes to what is the meaning of a cost? I typically take a different example. Let's say you need to go from here to Mysore. What is the cost? Anyone would like to answer? If I need to go from here to Mysore, what is the cost? Arpita ji, B.R. Gagan, BB Aisha.
Yes, sir.
Yeah. What is the cost from here to Mysore?
Around 1,000.
What way? How do you calculate that cost?
The running cost of the car, petrol or diesel.
Okay, so you are saying basically if I go by car, including my, how far is Mysore from here?
Around 100 to 150 kilometers, sir.
250 kilometers? No, it is way too high you are going. Anyone else can give better dimension? How far is Mysore from here?
150 kilometers.
150 kilometers, 140, whatever, something of that border. 200 is way too high. Now, if you want to go by car, how much diesel you consume? Even if you take the regular car, which let's say a high-end car, which takes about 10, which gives you average of 10 kilometers per liter, you are looking at about 15 liters of diesel, and that's about 1,000 rupees. So that's what you are looking at, perfectly fine. If you were to go by public transport by a train, cost maybe 400 rupees or 300 rupees or 200 rupees depending on the kind of bus you will travel. So one way to look at cost is only the money it costs you. There's another person for whom time is important and money is not so much important. I have my own plane or own helicopter. I like to go from there, but probably reach there in half an hour. So for me, important is what is the minimum time it may take me to go. If you look at the time criteria, if you go by your own plane or own helicopter or whatever, it may be half an hour. If you go by your own car, it may be 3 hours. If you go public transport, like train or a bus, it may cost you 5 hours, and so on and so forth. For somebody else, it may be comfortable ride. I want to make sure that I go a route which is scenic, in between breaks there. I don't care about time, I don't care about money, I care about enjoying my time. There are different criteria. Or something, whatever you can define. So cost is depending on the perspective of the person you talk to, cost would vary. And This happens when you ask someone to ask you how far is Mysore. For one person, it is 150 kilometers. For other person who is going by car, it is 3 hours. Kilometer doesn't matter. For another person, it is time, comfort, there's a different answer. So based on perspective, you look at different way of measuring, and term uses what is called a metric. How do you define the metric? How do you define the cost? It, or we can take a of some factor of distance, some factor of time, some factor of money, and arrive at a number. Maybe you can give 40% weightage to the distance, 30% weightage to time, 30% weightage to the cost, and arrive at a number, and that becomes a metric, and that determines. So using some way, we assign a cost to a link and say this is my cost. And once you identify a cost, which could be based on any other parameters, you use that cost to determine the path cost or how much, what the cost will be from source to the destination. If you have other criteria such as policies, like you may define that if I need to go from here to, let's say, Ooty, whatever we do, we cannot go through Mudimalai forest because there are elephants there, they may come and kill us. So cost is not important, the safety becomes more important. And cost becomes overriding factor. So when you decide upon a traffic, this policy also does play a role. But we will not bother about policy till we come to BGP routing. We will look at our link state routing and distance vector routing, OSPF. We look at the cost and we treat cost as a number. Now, how does my routing table look like? If you look at a machine, you look at a Windows, you basically say destination, what is the next hop, the mask to be used to identify the destination, and the interface on which the packet has to go through. And this basically defines the 4 columns: destination, gateway, mask, and the interface. Cost is not part of routing table. Cost is used to build the routing table, but once routing table is built, you use that, you don't look at the cost. So given that our connectivity of a graph, that means given that we have a number of routers that are connected by various links, how do we identify a cost? And to that we do mathematical modeling, and we model the network as a graph. So as you model the network as a graph, our routing problem primarily becomes graph theoretical problem, like using Dijkstra shortest path algorithm, the shortest from a given source to all other destinations, that is Dijkstra's algorithm. And we've seen that when we studied the algorithm course. So we can represent a given network. The network is nothing but a graph, where each node of a graph represents a router, and each link of a graph represents the each edge of a graph represents the link between 2 routers. It could be road transport link, it could be air link, it could be railway link. There are different things. We look at all those aspects and make a determination. Once we got a graph, that is each router corresponds to a node and each link corresponds to an edge, and once you build a graph, then we can apply any well-known algorithm to find out the given cost. Now the cost from between 2 nodes A to B would be equal to sum of cost of all edges from A to B. Because A to B may not have any edge, but if there are 3 edges from A to C, C to D, D to E, and E to B, then we add the edges, all these 5 edges cost, and that will give us total cost from A to B. Now once I got a network represented as a graph, I computed by computation, is it good enough for me? Do I need to recompute it again? Answer is yes, because network is a live entity. It can keep on seeing different conditions. Links may go down, links may come up. That often happens with you when you do 4G connectivity. Today network is not working, today it is working fine. So links go up, links go down. Same way, your router devices go up and go down. When network is down, That happens to be one of my numbers, idea numbers. Half the time I never get connectivity, so there's a link liability. So if we compute one-time cost when link was up, then that cost is not applicable when link is down. So new links come up, some links goes away, and and because of the link cost changes, we need to basically recompute the cost anytime the changes occur. Even the node cost, when you look at the graph, we can look at distance from here to whatever destination it is, but we are considering only edge cost. There could even be an host cost. Let's say I'm traveling from here to Delhi, going by my car. It's about 3,000 kilometers. I cannot travel non-stop, so I'll be staying in a hotel overnight. So in addition to my edge cost, the travel cost and my petrol cost, I'll be staying in a hotel and eating food. Those become my what is called the node cost. So total cost would be my node cost plus the edge cost of all the edges which I visit, and that gives me the total cost. So I cannot do one-time computation because new links can come up. We can design add new links, old links can go down, and same could be true for server. Node old server could go down, the new routers could get added. So primarily what you're saying is, because of the dynamic changes, my network topology keeps on changing. And because my topology keeps on changing, my cost keeps on getting updated. I need to update my cost. If I'm doing this process manually, the moment I notice a link change, I need to go and update all the routers in the network, the new cost, which is a cumbersome process. We need routing protocols that talk to each other router, and once they talk, they should build a convergent routing table. That means there should be no confusion. If node A got a packet for some destination, node A gives to node B, router B gives to router C, router C shouldn't give to back to router A, because then it will be a loop A to B, B to C, C to A, and so on. So routing protocol should converge. They should give me consistent result that if I'm getting a packet from A, it should go to B, it shouldn't come back to me, it should finally find a route destination where packet should go. So one is build, we need a routing table to talk to each other, build a routing table. Second is how fast they can convert, how fast each router can update the routing table based on the connectivity, and that is called convergence time. So we'll look at few examples of graph abstraction. We'll look at how to define the edge cost, and then we'll look at how can we use Dijkstra algorithm to find the cost from given source node to all other destinations. So given this graph G of n nodes and some E edges, it has about 6 routers. You can say U, V, X, W, Y, Z. And there are number of links edges as you can look at. And basically we are representing our network as a graph where each node U, V, W, X, Y, Z is a router, and these are edges. So we normally consider graph abstraction between any two nodes, we look at only one edge, not the multiple edges. Somehow with weighted factor, we need to get simulation, and between two nodes, we'll consider only one edge. We're also considering only undirected edge, but it can be directed as well, then we get a directed graph. But for our purpose, we look at only undirected edges. Undirected edges means if I can go from U to V on the edge UV, V can also come back to me on the path UV. And that's the meaning of undirected edges. If V is reachable from U, then U is also reachable from V, vice versa. And that is what we basically look at. So this model helps in our other networking problems, such as P2P, where each peer becomes a node, each TCP connection becomes an edge, and you build a model and look at which is the nearest, which is the farthest, and deal from there. So now we look at a typical how to find the cost. Consider that we know the cost, or we want to find the cost from U to Z. Our objective is we want to find the cost from U to Z, and we would like to look how the cost should be calculated. Now, the cost U to Z would be depend on the each of the S cost. I can go via this path, U to W, W to Y, Y to Z, or I can say U to W, W to X, X to Y, and Z, and so on and so forth. So these costs are basically a number which is somehow derived from some metric, some policy which a network admin had used. It could be statically configured, or it could be running some policy and reliability and the traffic bandwidth and delays. A router can say it is 1 byte delay plus 10 millisecond of 1 is 10 millisecond of delay for US universities plus reliability, other things. I look at those, and that gives me basically the cost. So my path cost from U to X, U to Z would be U to V, V to X, X to Y, Y to W, Z, or we can say U to V, V to W, W to Z, or there are a number of other paths. And when you try it out, you might be able to find close to about 17 paths in which a U can reach Z. And so we need to identify a path which has the least cost, and based on the least cost, we update the routing of X, indicating to the router that whenever you get a packet, you should always communicate with the proxy server with the whatever where I'm listening, and then connect upon. And then SD cost there. So our routing algorithm would be, we have different path there, find the path that has a minimum cost. And let's look at how do you find that minimum cost. Before we do that, we also look at routing categories, the protocol categories. One is called global or centralized, and other is called decentralized. So if it is global, meaning node U is connected to V, is connected to X, is connected to W. If does node U knows about the link YZ, or does node U knows about the link WY, that means if a node knows the entire network connectivity, that means W knows about the link U1, W knows about the link XY. So each node knows about the entire network topology, and that is what we call is link state routing protocol, when each node knows about everybody. And we look at how do they communicate this information to everybody. Link state means for status of each link, I have about how many links here? 2 plus 2, 4 plus 5 and 3, 7, about 9 or 10 links I have got. So each router knows status of all the 10 links, then it becomes the distance vector link state routing protocol. However, if a node knows only neighbors, you know that I can reach V, you know that I can reach X, you know that it can reach W, but it doesn't know beyond that. W can say that I can reach Z with a distance of 5. You will trust that, but you will not know whether W is directly connected or going via 3 hops, each with a cost of 1, 1, and 2. The distance vector routing does not need to know that, and that is called decentralized approach. That means router knows connectivity only about their neighbors and nothing else. They somehow get the reachability information in computation, what the distances from W to Z, W to Y are. They work upon those, and that is the one category. So first we look at link state routing protocol, and tomorrow's lecture we'll look at distance vector routing protocol, which belongs to the category called the decentralized protocol. Primarily, we look at the cost, neighbors communicate the cost. When you study tomorrow, we will know how to determine it. So today we look at link state and determine link state, meaning each router knows connectivity of each other router. So how do they know? I typically broadcast my information to others, and they determine. One simple way is, if network is small, like KSIT, which does not go through enough changes, then we can configure routing table statically manually, giving a command, save them, and since we know that change does not happen quite frequently, so we don't want to run routing protocol, because running a routing protocol is a costly phenomenon. You take too good amount of CPU time, and that would impact your routing performance. So typically, your N is the static routing. So because network does not change, the network administrator simply define it once, And it, like for KSIT, it may change only when a new lab is added or a new department is added. Then probably once in a year or once in 6 months you make change. And you don't spend any time in exchanging routing protocol packets. You don't do any computation. So nobody knows your topology. You save a routing cost. And also some way, because nobody knows your topology, in some sense of defense, because you're saving from the attack. But this static topology, the configuration does not work for a large network because there are too many devices, too many changes, and the large network with too many changes, static is fraught with error, and you cannot use static reconfiguration because then every 10 minutes you'll be doing some changes, and the life of network administrator would be hell. The other category of protocol is called sensitive or insensitive. That means based on the load. So if the particular network or a link path has a high load, should we choose other path? Ideally, it makes sense. If you know that from here, you want to go to Janagar and the Kanpura road is congested, you probably go via Subramanyapura internally, which is not congested. So if you can determine your cost based on the traffic or load on the link, that certainly user would want it. But doing such a thing is really very, very challenging. And we look at some example towards the end, which basically indicate if you were to define our cost based on the routing, based on the load on the link, our routing protocol will see too many oscillations and there will be no stability and practically no convergence. So how does a router run routing protocol and get a topology? Look at the link U. You will send the message. Its connectivity is U to W, U to V, and U to X. It will send 3 pieces of information indicating I have 3 links. UW link is 5, UV link is 2, and U1 link is X, and send this information to both X, V, and W. Now these X, V, and W know their own links. So W will broadcast this message to its neighbors. Same with B will broadcast and same Z will broadcast. Now if they broadcast further, so look at U sends a message which both goes to W and V to V. V will send to W, W send to V, will send to W back again, and it goes in a perpetual loop. To avoid that, each broadcast message contains some unique ID along with the router ID. So when we get the message, it will forward it once, but it stores in its memory. And next time it gets same message from W, it knows that I already forwarded it. It will simply ignore, do not do anything. So network traffic would be used for forwarding duplicate packets, but network, because it's keeping an ID and identify storage, it does not change. And that's the beauty of this routing protocol that basically helps when you broadcast, when I stored my ID, on the next new message, ID would be different. So for a one message, each node will send or receive one copy of it. Now consider a case that as U is sending its linked state message, meaning UW cost is 5, UV cost is 3, U1 cost is 1, UX cost is 1, and this message goes to WVX. They will further broadcast it if they are not broadcasted, and eventually each router will receive the message. So question I am asking is, when you send a broadcast message of connectivity, how many copy of the message Y would receive? Let me repeat the question again. When you broadcast this information on the link to the nodes V, X, and W, that my S cost are to W is 5, to V is 2, to X is 1. How many copy of this broadcast message which is sent by X is received by router Y? Anyone want to give a thought and give me the answer?
Two.
Can you explain why 2?
So
Your voice is not clear.
one from W.
Can you
One
repeat
from
again?
X and one
Yeah.
from W.
One from X, one from. Will it not receive from Z also?
Z also, sir.
It will receive.
Yes, sir.
Yeah.
It will receive from Z also. So I will receive a message based on how many the edges I'm connected with. But
Three.
look, yeah, three. So Y would receive three messages. If U sends message to V, W, and X send the message, W send the message. Now same message we will give it to X. V doesn't know whether X is received or not. And X, because I already forwarded it, it is stored in itself in the ID and does not forward again. Because if it forward again, then a perpetual loop. We keep sending to each other, the network would be choked. So link state messages are sent to the neighbors. Neighbors send to their neighbors, provided they are not sent already. They maintain a copy in their own memory. But if a new message comes from ye, then you will give IDs to, and those two will send again. Because when a new message comes periodically, there might be some new change, something they let you take care of. So because we are doing broadcasting, so each node would know the topology of the entire network. And once they know the topology of the entire network, you can basically make sure that we can run a routing algorithm. What is the network diameter? Anyone? A return call after diameter D, each node knows the topology. So what is the diameter D? What is the meaning of a diameter of a graph?
Divided into two planes from the center.
No, that is not a diameter. What is diameter of a graph? Would anyone like to explain what is the diameter of this graph? Diameter in the graph is what is the minimum length between the two farthest nodes. So if you look at U and Z, you will need how many edges? Two or three? Between any two nodes, can you go with two edges or do you need three edges? Between U and Z, how many minimum edges you need to reach? Two, three, or four?
Two, sir.
Two. You can go to U to W, W to Z. How many edges we would need between, let's say, X to Z? Again, two. So the diameter of a graph is basically two. That's the minimum path length you need between two farthest nodes. And what we're saying is, once anything is broadcasted, within the two broadcasting further, each network, each router would know the topology. So after D transmissions, each router knows. So let us look at how does my routing algorithm really work. When we said we work with link state broadcast, and because we are communicating in link state, each router has the same topology of the whole network. Because message would eventually reach, and once we get the topology, each router computes the distance to other routers and builds the network, and that is how the Dijkstra algorithm basically works. And if we start with a particular source node, we start with the source node, and each time we pick one node which is closest, keep picking it up, and after about k iterations, we picked up k nodes. So if there are n nodes in a graph, we basically do the loop iteration. Now to understand our algorithm, we define certain notations. First is the edge cost. If there are two nodes x and y, edge cost is equal to whatever the edge cost is. For example, given node the different values, or it is infinity. So if you were to go to my previous graph, what is the edge cost between V and Y? edge cost between node V and Y?
Three, sir.
3, sir.
V and Y edge cost. I'm saying I'm not asking a path cost. I'm asking
Zero,
the
zero,
edge
sir.
cost. You want to sum V to Y, I can reach with the zero cost? No. V to Y, there is no edge. And because there is no edge, I cannot reach directly. I need to go either Vxy or Vwy or Vux or whatever way, or Vuwxy, a different way. So my edge cost between V to Y is infinity because there is no edge. So we define our edge cost. If there is a cost, we define that value to Y or define it infinity. Each node also maintains a vector called dv, which indicates the distance to that node so far. And we also maintain a called predecessor in reaching that node, through which predecessor node we would be reaching. We'll maintain these three notations, and using those, we'll figure out how to compute our shortest cost path. And one will maintain a set of nodes for whom edge cost is already detected. We know what the shortest cost is. And once we add a node to n prime, we are not going to use that node again. So algorithm works in two parts. One is called initialization, and next is the looping. So initialization, we basically initialize my distance vector dv. So for all the edges, whatever my edge cost is, I'll define to be the edge cost. If there is no edge, I define it to be infinity. Having done this initialization, we do in a loop. And what we do is look at all those nodes which are not in n prime. N prime is the set of nodes for whom I have already computed the cost. So in initialization, when I start with the node u, I make n prime as that node. And after that, I'll keep looking at all those nodes which are not in n prime, which is closest to me, and add to n prime. So I look at the nodes w which is not in n prime, but whose dw is minimum. And once I find that node, I add that node w to n prime. And now using w, I update my cost, all the dw. So let's say from a given node u, I want to know the cost of v because w is added. So either the distance to v is minimum, or I look at my edge cost to v, my edge cost to w, and my probably the weight of distance of w. And if whichever is minimum, I update that and then go to the loop again. So I basically do two steps. One is find the node n, find the node w, or any node which is not in n prime, whose dv is minimum, add that node w to my n prime, and then for the node I picked up, look at all the distance vectors and update the value with respect to node u. So, and then look at, update the minimum, and that is basically my logic. So we'll run with an example and you'll probably see. Let's say this is my graph consisting of 6 nodes. I start node is u. So I start from the node u. When I start from the node u, what would be my dv, dw, and dx? dv would be 7, dw would be 3, and dx would be 5. Because u to y there is no edge, u to z there is no edge, so I'll keep the distance to infinity for those two nodes. And this is my initialization. Having done this initialization, look at all the nodes which are not in n prime. My n prime is u, what I started from. All the other nodes are this. Find that node v for which this dv is minimum. So which is the node which has the minimum value among all the n prime so far? would like to answer. Among these 5 nodes, V, W, X, Y, Z, these nodes are not in unprime. V, W, X, Y, Z. So pick a node whose DW value is minimum. So which is the node whose distance vector is minimum for you?
W.
Yeah, anyone?
Path to W, sir.
W, because if I look at the node DW is 3, DV is 7, DX is 5, that's an infinity. So I pick the node W and add the node W to my n prime. Now I need to update dV, dx, dy, and dz. Currently my dV is 7. My cost from U to W is 3. And what is dW there? So if you look at my dW is 3 and cost from W to V, the S cost is 3. So dW is 3 and S cost is 3. So dW 3 plus S cost CWV is 3. This becomes 6, but previously V is 7. So we look at the previously miniaturization, U to V, my dV is 7. But my dW is 3 and H cost from W to V is 3. So dW3 plus 3 is 6. So that means my dV becomes 6 because this is lower. Does my X change? My dx is 5, my dw is 3, S cost is 4. So 3 plus 4 is 7, which is more than my dx. So we don't update dx. What about dy? dy was infinity. Now my dw is 3 and S cost from y to w to y is 8. So 8 plus 3 is 11. That means my dy would become 11, and that is what we had done. Can you compute dz? Will the dz be updated? Look, from w there is no h to z. Because w there is no h to z, this cost will remain the same, whatever it was before. Because this is from 10 point, whatever my cost is, and I'll maintain that cost. I updated, so now my among these nodes, dv,
Sir,
dx, dy, and dz.
sir,
Yeah, go ahead.
sir, for Z we have Y, no, sir. 2.
We repeat again.
For
For
Z,
node z, yeah.
yeah, we have
Look,
Y.
look, I started, let me start again. Okay. Is this part clear?
Yeah,
Now, which is the node with minimum value? dw is minimum,
yeah, 3.
3. So I pick the node w, add it to n prime. Is that okay?
Okay, sir.
Now look at all the edges from w. W has edges to x, it has edges to y, and edges to v. And dw is 3. So if I were to go to x via w, my cost would become 7, where it is 5. If I were to go to v, my dw is 3 and w to y, v is 3. So if I go to v, my cost would become 6. If I were to go to y from w, it will become 11. Is there a s from w to z? No.
No, sir.
Correct? That means
Yes.
I look at the only node x, y, and v and update their edges. Look at the algorithm. Whichever node I pick up, look at all the edges from that node and add that value and look at the previous value. Whichever is minimum, so look at all the node for all the node V which are adjacent to W. I pick a node W with a minimum DW. Having picked W, look at all the edges WV. That is all the nodes which are neighbors of V and update that DV. Either previous value or DW plus the S cost. So when I come here, I pick pick W, add it to it. Now from W, there are three edges, WX, WY, and WV. If I were to reach X via DW, it is 3 plus 4, 7. I know my DX is already 5. I don't need to change. And I'm reaching via U. If we look at in this first line, VWX at cost was DV is 7, DW3, DX is 5, and I'm going via U direct. Now when I come to the V, my DV was 7. But if I come via W, DW is 3, S cost is 3, so via this cost becomes 6. I update it 6 and say, to V I can go via W. I update it 6, comma W. But for Y, I had cost was infinity. Now my DW is 3, W to Y is 8, it becomes 11. And predecessor is W. Is that okay?
Yes, sir.
Now which is the node which is the minimum DW? Which is the minimum among the four nodes? I have two nodes in N prime U and W. Remaining are V, X, Y, and Z. Which is the minimum among here?
5, sir. 5.
5. So that is node X. So I add U to my N prime now. And what are the edges from X? Already U is there, so I don't look at it. Already W is there, I don't look at it. So edges are Y and Z.
Z.
So I'll update it now. Look, what is my weight to dx is 5. X to Y is 7. So if I were to go from X to Y, it is 5 plus 7, which is 12. But already my dy is 11. Does it get updated? So dv remains the same because X to V, there is no edge. So dv remains the same, which is 6, comma W. W and X are already in the node, I don't update them. Does Y get updated? My Y is previously 11. My dx is 5 and X to Y is 7. So 5 plus this 5 plus 7 is 12. But already my dx is 11, so I don't update it. But look at Z. My previous dz is infinity. My dx is 5. 5 plus 9 is 14. I update it. Is that okay? Are we fine here?
Yes, sir.
Now, among these three nodes, V, Y, and Z, which has a minimum value of D?
6.
6. That means we pick node V and add the node V to N prime. And now look at the edges from V. Edges from V are to U, to W, and to Y. U and W are already part of my N prime. So this cost is not going to change. I'll look at only Y. What is my dV value? What is my dV value?
6.
6. Don't look at the edge. Edge may not be there. My dV value is 6. My dV value is 6 and V to Y is 4. So if I were to go to Y via V, my cost would be dV of 6 plus 4, which is 10. What is the previous Y value? 11. dy is 11, but if I were to go via V, my dV is 6, dV is 6, and S cost V to Y is 4. So 6 plus 4 is 10. That means I'll update my dy to be 10. And because I'm going via V, I'll update my predecessor node as V. Now look at, does this dz change? No, because V to Z there is no edge. Now I have two nodes V and Y and Z. Minimum happens to be 10 corresponding to Y. So I add Y to my N prime. Now from Y I have edges to X, edges to W, edges to V, and edges to Z. All these nodes X, W, and V are already there. They're not going to get updated because once I pick a node, the cost does not change. I look at the now, what is my dy? dy is 10.
10, sir.
10.
10, sir.
As to yz is 2. So yz as is 2, dy is 10. That means if I need to go z via y, my cost becomes 12. And previous happens to be y. So I'll update it, becomes 12. And the last node I pick up, I computed everything. So I know the shortest path, cost from U to W is 3, go directly, U to V is 6, predecessor is W, U to X is 5, which is directly, U to Y is 10, and before Y comes V, U to Z is 12, and before Z comes 12. So I can build my basically distance path. I look at each node, I look at Y, and Y, I look at Z. Z means come via Y. So I draw the edge YZ. I look at the node Y, Y is coming via V, I draw the edge VY. Look at the edge V, V I'm coming via W, I draw the edge W. X I'm coming directly, and W I'm coming directly. So you define the path, and this indicates the cost. And that's how the Dijkstra algorithm runs. Any questions about this? So I would say look at it. You can work out another example there. So I worked out the example, but I would say work it out yourself. Let's say initialization, again I start from U. So I will have a 1, 2, 3, and others would be infinity if you look at. And then update again and again. Work out and say you pick this one, update the U. So my minimum is X. I add X to N prime, it becomes UX. And from X, I have a path to V, a path to W, path to Y, and path to Z. Now look, what does dx is 1 and x to y is 1, so my dy would become 2. Similarly, if you look at the dx is 1, x to w is 3, so u to w would become 4 because 1 plus 3 is 4. And that's how the cost would be added. And you keep repeating, build it. So the question I'm going to ask you, I'll give you a graph with S cost and ask you to work out this Dijkstra algorithm to find the minimum cost. And that is what we were doing. So work out yourself, look at the exercises. If you still have issue, then ask me questions. I'll go through remaining part. You can look at another example, the same example, but how the path will look like. You change the cost, work out, and you would know. And when I'm going to ask you a question, your S cost would be depending on US and 4-digit something. So different people have a different graph. And to work out that cost and give the answer. And that way you can build your destination, the predecessor path, and what the routing cost would be. And that's how you build up. So primarily look at the discussion, what happens each time I iterate. So let me go to my algorithm there. This is my algorithm. Each time I pick a node, I find a minimum amount remaining. So time taken to pick a minimum is order n, because there could be n nodes. So first time I do n comparisons, next time I'll do n minus 1 comparison, next time I'll do n minus 2 comparison, because my nodes left are minimum. To find a minimum, I will do order n work, and I'm doing this for n times, because my loop runs n times. So time complexity is n square. Even once I pick a w, for each of the adjacent node to w, which could be n node, so I may be doing again n comparison. And since I'm running a loop n times, again my time complexity is n square. When you look at Dijkstra algorithm, time complexity is n square because we are running it. That is using adjacency matrix. If you were to use adjacency list, we do adjacency list, then time complexity will be m number of edges, log n, because you can make a heap. And in a heap, when you update the minimum value, adjustment takes order log n time. And you do for each edge, because each edge you consider only one. You don't consider again, and each time you can update the heap, so it becomes log n. So depending on implementation, complexity could be n square or m log n. Can there be oscillations? As I said, if you were to take a load traffic into the account and decide the cost based on that, then I could see oscillations with each iteration. My routing cost will keep on changing. Look at a simple graph of 4 nodes A, B, C, D, and say 3 nodes B, C, and D want to send their traffic to A. D sends 1 unit of traffic, B sends 1 unit of traffic, and C sends E unit of traffic. When that is the case, let's look at C sending via B. And if I'm taking my edge cost as amount of traffic, so the edge cost C to B is E, edge cost B to A is 1 plus E, because B is sending 1 unit and C is sending E unit, which is going via B. So this edge is seeing a cost of 1 plus C. On this side, there is no traffic, so cost is 0. This sending the traffic 1 unit 1. So this is my cost. So edge cost D to A is 1, B to A is 1 plus E, C to B is E. So if I were to do rerouting, if I were to do rerouting now, what it will look that C on this way C to A, my cost becomes E plus this, and if I were to send traffic like this, it basically becomes this direction is 0, this direction 0, this direction is 1. So in this direction, cost is 2 plus E for C. In this direction, cost is 1. For B, this direction, cost is 1 plus E. So you look at what's happening. This cost is 0, this cost is 0, this cost is 1. But this direction cost is 1 plus E. So next iteration, everybody would follow this path, and that is what you are seeing. When this happens, look at my link cost. This traffic is 1, as cost becomes 1. This traffic, C is sending E unit of traffic, B is sending 1 unit, so this becomes 1 plus C. 1 plus C traffic, D is also sending 1 unit, this becomes 2 plus C. And this edge is 0, this edge is 0, from D to C is 0, C to B is 0, B to A is 0. That means next time we compute, whole thing will go this way, because this way cost is 0. So we'll recompute, update the cost, and next time we send traffic via this path. The moment send traffic via this path, this cost becomes 1, this cost becomes 1 plus C, this cost becomes 2 plus C, and traffic in this direction is 0, we'll again recompute. So you see, because traffic is changing, we keep changing our link cost, and we keep updating routing table with each iteration, and that is called oscillation. So if we were to define the link cost based on traffic, oscillations would occur, and this is a tough problem. So typically in any network routing, you don't look at traffic to different routing costs, because that will cause too many fluctuations, and that doesn't work. So you define a hop cost or link cost based on the number of hops, number of what is the bandwidth value. Traffic you normally don't use because that gets too complicated. What is the delay? Link reliable or not? You can give a factor or a combination of those, and that is what you do to define the cost or monitor. So you can work out the exercises, take a different graph, work out, and make sure you understand the way things work out. The few quizzes: should I use static routing versus dynamic routing? If you use static routing, what is the benefit you will get? Because you use static routing, you are not doing any routing advertisement. That means nobody knows the topology. So chances somebody attacking you would not be there. So you become more secure. And because you are not doing any computing, you don't fix computing, there's no computing. So it's more secure and no computing overhead. But the basic issue with static routing is network changes too much. Your network admin job throughout the life would be keep doing it and unscalable. You cannot scale it. It does not work for a large network. Same way, convergence time means time it takes to stabilize. Like we said in the link state routing, if a network diameter is D, within D much is a broadcast, I'll get my topology done and I can compute. So convergence time is time taken to update my routing table and get consistent information. So that is what my convergence would be. So these are basic terms. These two questions are from the textbook. You can look at and go through that. And then you basically summary. So we look at link state, meaning each router in the network knows the topology. They advertise using broadcast messages. A router advertises only if it has not advertised earlier. So each message keeps a broad message ID, router ID plus message ID, it stores and forward only when it does not forward it so far. And that will make sure that each router get the message. Once you get a message, you compute the cost using Dijkstra algorithm and then work out, and that's the way algorithm works. If any questions, you can feel free to ask. Otherwise, tomorrow we'll discuss second category protocol called distance vector routing. I am done. Thank you. If you have questions, please feel free, or we are done.
Sir, we
Thank
had
you, sir.
questions for
Go ahead.
regarding assignment, sir.
If you have a question regarding assignment, then you have to probably send me a message and then I'll call you. I had a session yesterday. Were you not there? We had a session yesterday. Did you not join?
Sir, is there